So good afternoon, everyone. Welcome to this is the third installment of our mini school on a practical introduction to quantum computing. And again, we are lucky to have Ian with us, who is an expert quantum computing programmer. Yeah. So Ian, thank you very much for being with us and for preparing this very nice course. Yeah. So please, without any further ado, Ian, if you need to share the screen, you're most than welcome to do it. And to the participants, this is set up, the mini schools are set up as meetings. So please, if you have questions, just unmute yourself and ask the question. Yeah. And after the lecture, if there will be more questions, we won't record those. Yeah. So if you have urgent questions in between, that's fine. But in order to encourage people to ask questions more liberally, we usually don't record the question session at the end. Yeah. So Ian, please, you're most than welcome to start. Thank you. Thank you very much.
Thank you, Prof. Thank you. Let me actually start sharing my screen. Good afternoon to everyone here, and welcome back to lecture 3 of the mini school on quantum computing, a practical introduction to quantum computing with Qiskit. As promised last week, this week I'm going to talk a little bit about Grover's search algorithm and how to implement it in Qiskit. I think most of you here might know about Grover's algorithm. I think it's pretty well known, and it's one of the key quantum algorithms that you will study if you're doing an introductory course on quantum computing. So I'm not going to go too much into the algorithm today, but what I'm going to do is just give you a brief overview and show you how you implement it in Qiskit. And thereafter, I'm going to give you an example of how you can use Grover's algorithm to actually solve a very simple binary Sudoku problem. And it's very interesting. I think usually we just see how to do it for the computational basis states, but to actually use it to solve an interesting problem, I think would be pretty cool. So let's start. Grover's algorithm is an algorithm that basically provides a speed up to the unstructured search problem. So unstructured search, meaning that you have a database of n elements, and you wish to find an element in that database, and there's no ordering to it. So it's not ordered alphabetically or anything like that. It just has no structure. And Grover's algorithm provides a quadratic speed up to the unstructured search. But what's really interesting about Grover's algorithm is that in doing in giving us the quadratic speed up, it uses something called the amplitude amplification trick, which has actually become a lot more useful in other quantum algorithms. And it's been shown to give us quadratic speedups in other algorithms. For example, if you're doing Hamiltonian simulation in the linear combination of unitaries approach, and even simulating by truncated Taylor series, they use the amplitude amplification trick to actually simulate specific Hamiltonians. And you can read more about that if you just do some searching on Hamiltonian simulation. But that's just an example of where we use this amplitude amplification trick in other algorithms. But today we're just looking at Grover's algorithm. So we'll first look at the unstructured search. As I very briefly described, we have a database of n items, and we want to find one unique winner. So we call it a winner because it's the solutions. That's what we're looking for in our search. And basically, if we draw it out, it looks like this. And usually this capital N, or the number of items in our database, is usually, we can write it as some 2 to the n. And if it's not a power of 2, then what we end up doing is we just pad it. So you have, like, if n is 3, we just use 2 to the 2. So we use 2 qubits to store our database, but that's just an aside. And the goal is just, if we were to locate the winner or the solution of our search in this database, then on average, we would have to check, in the best case, n over 2 boxes. We'd have to go and perform n over 2 operations just to find the winner. But in the worst case scenario, we'd have to actually check all of these boxes to find the winner. And of course, if n is 100, right? On average, in the best case, we might have to check 50 boxes, but in the worst case, we check 100 boxes. But using Grover's algorithm, we get a quadratic speed up because we only need square root of n steps to find the winner. So we're not checking square root of n boxes, but using square root of n steps to in Grover's algorithm, we can actually find the winner. So for reference, as I said, if n was 100, we'd only need 10 steps to find the winner in our database using Grover's algorithm. So that's just an example of how you get this sort of quadratic speed up with Grover's algorithm. So, to implement the Grover's algorithm, like many other quantum algorithms, you need an oracle. So we're going to talk a little bit about the Grover oracle. And, for the purpose of this tutorial, the database that we're going to consider is just going to be the computational basis states of your n qubits, in little n qubits. So for example, if we have 2 qubits, then our database is just going to be the 4 computational basis states. So what the oracle does is the oracle is actually going to flip the sign of the basis state that corresponds to our winner. So if this is our database, one of these states is going to be the winner or the state that we're looking for. And the oracle, when applied to each of these basis states, if we have the winning state, then what it'll do is it'll flip the sign of that state from a +1 to a -1. So we call this phase kickback, and you'll see more about this a bit later. But effectively, if we write down our basis states in this notation here, where x goes from 0 to n-1, and then we convert those decimals to integers, we get each of these computational basis states. And if we denote the winner as being w, and that's one of these basis states, then the oracle is some unitary operator such that when it acts on each of the basis states, it leaves it unchanged if it's not the winner, and it adds a minus sign to the state that is the winner or the solution state. So, if you were to just look at this oracle, very specifically, it would be a diagonal matrix whose entries are -1, which corresponds to the state that is our solution, and 1 everywhere else. So for 2 qubits, if we want the winner state or the solution state to be just 1, 1, then this will be what the oracle looks like. And of course, if you know any quantum computing, this is just a matrix representation of a controlled Z gate. So for problems that can be solved by an oracle like this, we have to construct some function f of x such that it's 0 when x is not the winner state, and 1 when it is the winner state. So this should be x is equal to w. That's just a typo. So this allows us to then go and write our oracle in the following way. So we can write it as this unitary operator acting on our computational basis states is the same as -1 to the power f of x on x. So of course, if x is the winner state, then this is going to be 1, so you'll add a minus sign to the state x. And the matrix representation is going to look like this. Okay? With just -1s on the diagonal, and they're all raised to the power of the f evaluated at that computational basis state. So now that we know what the oracle for doing search problems in a database that is the computational basis states, let's see how Grover's algorithm basically will solve the unstructured search problem for this database. So the algorithm is as follows. The first step is all the qubits are initially in the state 0, and we need to place them in a uniform superposition. So we do that by applying Hadamard gates to all of the n qubits, and we call that state S. Then we apply the oracle to the state S. What this is going to do is going to flip the sign of the state that is the winner. So I write it like this, and this is just, it's going to be a sum on all the basis states. There should be another normalization factor here, but you get the point, is that this is going to be all of the basis states except the winner, and you have a minus sign on the winning state here. So there should be a 1 over square root 2 in the front here. Once we've done this, what we do is we then apply this diffusion transformation. This actually reflects about this S axis, so that we basically place everything in a uniform superposition. So all the amplitudes are all equal, and then we perform a sort of reflection that, when we reflect it back, amplifies the amplitude of the winning state. And we do this with this diffusion transformation, which is given in this representation here. And in general, we can construct a diffusion transformation, the circuit for this diffusion transformation. And it's very easy to actually construct this because we know already what the state S looks like. We just need to take the outer product of S and S and then minus identity, and you multiply by 2 there. So, if we just consider the definition of S, we can obviously write it like this with Hadamard gates on either side. And we can factor out the Hadamard gates because, of course, H tensor N times H tensor N is just identity. So it's fine to actually factor it like this. And we need to look at this matrix that's left in the middle here. So if we let this U naught equal to this middle matrix here, then this is what it's going to look like. It's going to be just a 1 on the first entry, and it's only diagonal with negative 1s everywhere else. So if we observe that we can use some multi-controlled Z gate, so that's a Z gate that has controls on the first n-1 qubits, and then it applies a Z to the nth qubit, then we see that that type of gate will add a negative phase to the last entry in our computational basis states. That is a computational basis state that has n ones in it. And if we add, a global phase, so we multiply by a global phase to our multi-controlled Z gate, we get a matrix that looks like this. And it's a matrix where the first n-1 entries in the diagonal are all -1, and the last entry is a +1. We can add a global phase because when we measure, it's not really going to do anything. And by using the gates X, with a tensor exponent n, this is just a permutation matrix. We can then flip, or we can permute all these entries so that we have a +1 on the top and -1s on the rest of the diagonal. And algebraically, if you're doing some algebra with these operators, what it'll look like is you have U naught is just going to be X tensor n there, e to the I pi on the multi-controlled Z gate with X tensor n on this side. And you get a phase of -1, and that's what your U0 can be decomposed into. And of course, if we want US, we just put the Hadamards on either side here. And we ignore the -1 again because it's a global phase. But this is actually what the generalized diffusion transform is going to look like for n qubits. So in circuit notation, this is what it looks like. If you have n qubits, US is just going to be Hadamard, then X over all the n qubits, and you're going to get a control Z, X, and then the Hadamard again. So after pi times the square root of 2 to the n, this is square root of n. So pi times the square root of n iterations of steps 2 and 3, the system has the highest probability of being in the state W. That means after applying step 2 and step 3, which is the Grover operator, after applying that for this number of iterations, then what we would see is that the amplitude of the solution state is going to be increased while the others will be decreased. And that's to preserve the probability so that the sum of the squares of the amplitudes are going to be 1. So the full Grover circuit is just going to look something like this. We start with everything in 0. We apply the uniform superposition. We apply the oracle, which will flip the sign or do the phase kickback on the winning state or the solution state. We apply the diffuser, and we repeat that this many number of times, and we measure. And when we see, we'll actually get that the probability of, if for example, we want to look for the state 1-1, the probability of being in the state 1-1 will be the highest. So let's look at a very simple example, which I'll implement in Qiskit. And that is if we have a 2-qubit system so that, our database consists of 4 entries. It's all the computational basis states. And we want to find the state 1-1. So when we want to find the state 1-1, we need to actually construct the oracle that will actually flip the sign of this the state 1-1. And to do that, this is what the oracle will look like. It's just going to be a diagonal matrix like this. But this is easy to see that this is just a controlled Z gate, because you can, of course, write this as a 0 outer product with 0, tensored with identity plus 1 outer product with 1, tensored with the Z gate. So we can see that this is a controlled Z gate. And when we actually put in 4 here, what you'll get is pi over 2, and approximately 1 iteration of the Grover operator here should actually produce or should actually leave us the probability of being in the state 1, 1 being the highest. So let's actually go to Qiskit and actually try to implement this. So we're aware of what the imports that we need are. There are 2 new imports that I'm using here, transpile and assemble, but I'll get into that when we get into the next part of the lecture. And we're just using NumPy. So we construct a quantum register and a classical register with just 2 qubits in the quantum register and 2 bits in the classical register. And we have a quantum circuit, which is just the quantum and classical registers. And then we actually prepare our qubits in an initial superposition like this. So this is a uniform superposition of 2 qubits. And once we've actually done, we do this by just applying Hadamard to the first and second qubits. And as you can see, we've drawn that. And then if you want to construct the oracle, remember I said that the oracle is just going to be a controlled Z gate. So we'll just place a barrier between our uniform superposition, and we put the oracle in here, which is just this controlled Z gate. And I'm doing that using this CZ gate here. And then I can apply the diffusion transform. So for 2 qubits, we know that the diffusion transform is just going to be x like that, a CZ in the middle, X is here, and Hadamard's on either side. So that's what I've implemented here directly in Qiskit. I place another barrier just to separate the diffusion transform from the measurement, and then I measure both the qubits. Now I'm going to actually run this circuit for 8,192 shots. I'm going to use the QASM simulator, and I'm going to get the counts. Once I have the counts, I'm going to plot the histogram. Now I expect that we have the highest probability of our 2 qubits being in the state 1, 1. That means I've actually solved the unstructured search problem using Grover's. And if we look at the probabilities, we see that there's a probability of 1 of being in the state 1, 1. So what we've done is after the Grover step, we've actually gone from a uniform superposition in the beginning to only being left with a state 1, 1 at the end. And that has allowed us to solve the Grover's search problem, or at least for this very basic database. So I have an exercise here that requires you to actually do this again, but the state that you're going to find is not 1, 1, it's 0, 1. So now the only difference is going to be the oracle is not going to be the same, and you need to find a circuit that actually implements that oracle, and then you just replace the step with the oracle here, and you should actually get the state 0, 1 with the highest probability in the end. And another exercise that I have here is to do it for 3 qubits. So you repeat the same process, but you just have to find a new oracle now that actually marks this state for 3 qubits. Now you're going to get an 8x8 matrix, and you need to find a quantum circuit that implements that oracle as well. But for both of these exercises, you're going to need a function that will actually implement a more generalized diffusion transform. So given the number of qubits, it should construct the circuit for the diffusion transform. And effectively, that's what we've written here. It's an exercise, but I'll just provide it to you. And this circuit is actually going to implement the generalized diffusion transform. So just to show you, if we have 4 qubits, this is what the diffusion transform will look like. And if we make this 5, you'll see that we actually get the 5 qubit diffusion transform. Now, the reason there's no control Z here, and you have a multi-control Toffoli with Hadamard's on either side, is because we're decomposing it so that we can write Z as HXH, and then we just need to multi-control just the X. So that is effectively what we're doing here, and this gives us a very generalized way to do the diffusion transform for doing Grovers on any number of qubits. So you can actually play around with this and try to do Grovers for 3 qubits or even 4 qubits if you're feeling adventurous, and you can construct the circuits for the oracles for the mark states that you choose. Okay, so that's basically what I want to talk to you about, the overview of Grover's algorithm. And in the next part, what I'm going to do is I'm actually going to show you how we can use Grovers to actually solve a binary Sudoku problem. Now, something important to note, and I should note I've taken this from the Quizkit textbook. So if you're interested in reading in a bit more detail, you can look into the Quizkit textbook for this this example. So far, we've always created our oracle with a prior knowledge of which state we're looking for. So when our database is just a computational basis states, we have a knowledge of what we're looking for and how to construct the oracle. But there's many problems in which we don't actually know what we're looking for, but we have an unstructured database and we have sort of conditions for which the solutions, or for which the winner state should satisfy. For example, if you're searching a list and you want to find a list of numbers, and you're looking for a number that's actually less than 50, then that's a condition. And you want an oracle that would actually show you, in your database, which variables in the database or which elements in the database actually satisfy that condition. And that's what we're going to do with the binary Sudoku problem. So let's consider just a 2x2 binary Sudoku. And it has very, very simple rules. No column can have the same value twice, and no row can have the same value twice. It's very, very simple. And it's called a binary Sudoku because all these variables V0 to V3, they can only be 0 or 1. So that's why we're calling it a binary Sudoku. And we want to basically solve this. Now, of course, this is a very, very easy problem to do in your head. So, clearly you can see that the solution to this will be to place, to use the diagonals. So you go 0, 0, 1, 1, or 1, 1, 0, 0. That'll be the off the top of my head, I can see the solution. But we're looking at this problem to actually just demonstrate how we can use Grover's algorithm to solve a problem, a decision problem, and to construct an oracle for this type of decision problem. Okay, so we want to create a circuit that will output the solution to the Sudoku. And it's very simple, but it's very interesting as well. So let's turn this problem into a circuit. So the first thing we want to do is we want to create an oracle that will solve this problem. And we do that by constructing a circuit that will identify the correct solution. So how do we know when something is a solution? Well, the values of V0 to V3 will be such that they satisfy the conditions that no column will have the same value or no row will have the same value. So let's actually take these rules and cast them into conditions on our variables. So considering the fact that no row should have the same value, V0 and V1 should not be the same, and V2 and V3 should not be the same, so which we have here. Then if we consider the fact that no columns should have the same values appearing twice, then V0 and V2 should not be the same, and V1 and V3 should not be the same. So we want a circuit that will actually, when we check these it should check these variables and see if it satisfies these conditions. Well, if we assign each variable here to a qubit in our circuit, then we can use the XOR gate to check if they are the same or not. And if you recall from classical computing or even a course on logic, you know that the XOR operation is going to be 1 if the two inputs are different, and it'll be 0 if the two inputs are the same. So the circuit that will implement an XOR gate will look something like this. So for two qubits X and Y that are given like this, and for some output state that's initially in the state 0, if X and Y are going to be the same, then what will happen is it'll leave this here as 0. And if X and Y are different, then it'll actually flip the state of the output qubit so that we have it in the state 1. So far, are we clear on that? Is everyone clear on where we are so far? Okay, I'm gonna take take that to be a yes. And now what I'm going to do is we're actually going to use this idea of the XOR gate to check each of the 4 conditions. So what we'll do is by storing each of the 4 variables in qubits, and then by using this XOR gate to actually check each of these conditions above, and we have qubits that actually we use to store what we'll call the clause, which will be whether or not the 2 variables are the same or not. So for example, if we have 4 variables, we need 4 clauses. So if we want to check if V0 and V1 are the same, then we have to check the value of C0. And what does that mean? If these are different, C0 should be 1. If these are the same, C0 will be 0. So we repeat that by just applying these C naughts between the things that we want to compare. So the second condition was that V0 and V2 not be the same. That's why I have 2 C naughts here. And to check whether they are the same or not, we use C1. And we do the same thing. We want to check V1 and V3 are the same or not. And we need to check the value of C2 if it's 0 or 1. And lastly, we need to check if V2 and V3 are the same. So we'll check the value of C3. This is going to be called our checking circuit. And it's going to check if a given binary string of zeros and ones, V0 to V3, satisfies the conditions to solve our Sudoku problem. So we're going to call this our checking circuit. And of course, we can actually simplify this by actually checking, instead of checking all 4 clause qubits, if we use a multi-controlled Toffoli gate and we apply it, the Toffoli to the last qubit out 0, then if all 4 of these clause qubits C0 to C3 are in the state 1, then out 0 should be in the state 1. And that tells us that we found a solution to our Sudoku problem. So we want that all of these conditions are satisfied. So that means we want all these qubits to be in the state 1. And if all of these are in the state 1, then we should apply X to our out 0 gate. So by checking if out 0 is either 0 or 1, then we can actually determine whether or not we have a solution to our Sudoku or not. So if it's 0, we don't. If it's 1, we do. So this is the full checking circuit that we're going to consider. And this is going to check the conditions of our Sudoku problem and tell us if our variables or the state of our variables V0 to V3 satisfies the Sudoku problem. But of course, the checking circuit doesn't completely make up our oracle, because to be a Grover's oracle, we need something like phase kickback. So next, we need to talk about uncomputing and completing the oracle. So I'll explain what uncomputing is in a moment. For now, just bear with me. But to turn this checking circuit into a Grover's oracle, we need to use phase kickback, which means we need to add a minus sign to the state that corresponds to a solution of our problem. So before we can do that, we need to actually do a quick recap on what registers we have so far in our quantum circuit. So we have one register of qubits, which will store the variables V0 to V3, and we call that register X. And this is what it looks like. And then another register of qubits is used to store the clauses, so that those are the values of C0 to C3. And these all start in the state 0. So how we'll represent it is we'll just use the 0 bar, which is defined as just the tensor product of 4 states or 4 kets that are in state 0. And lastly, we have one qubit called out 0, and this just stores the output of the checking circuit. So those are the 3 sort of registers that we have so far. So to create an oracle, we need, this unitary operator UW, which is that where W is the winning solution. This oracle should perform the following transformation. When this oracle actually acts on the state of the 3 registers, we need to get that it actually does out 0 addition modulo 2 with f of x, where f of x is 0 if x is not a solution, and it's 1 if x is a solution. So if we actually set this out 0 to be the minus state, which you've seen in previous lectures, this is just 1 over square root 2 on 0 minus 1, then this is what the action of the oracle actually looks like after doing a bit of algebra. So what this actually gives us is that we will actually get that the action of the oracle on our three registers is going to be the same register if f of x is 0, and it'll actually be minus a -1 times the initial register if f of x is 1. So there we go. We found a way to include phase kickback with this oracle. But what does the oracle actually need to do? Well, if we want to adapt our checking circuit that we created above into a Grover's oracle, then we see that what we need to do is that after we actually apply our checking circuit, the state of our clause qubits, so the C0 to C3, actually needs to go back to being all 0. And the way we can fix that is by actually repeating the checking circuit. So by that I mean repeating this portion of C naughts here, and we call that step uncomputing. So what we actually have in the end is we have a full circuit that looks like this. And this is the Grover's oracle that will solve our binary Sudoku problem. We first use the checking circuit here, and we check the values of the clause qubits. We store it in out 0, and we uncompute so that all these clause qubits actually end up back in the state 0, 0, 0, 0. This is going to be the oracle that we're now going to put into our Grover's algorithm. And in summary, what we see is that the action of this oracle is just going to be, it's going to be the same thing if X is not a winner or it's not a solution to the Sudoku, and it'll apply X to the out state, out 0 state if X is a solution to the Sudoku. And of course, we've already set out 0 to be the minus state. So this is what the action of the oracle looks like on our 3 registers. So now let's go into Qiskit and actually implement this. So to actually do this, we need to actually store clauses or what we want to check in a list. So we want to check if 0 and 1 are the same, 0 and 2 are the same, 1 and 3 are the same, and 2 and 3 are the same. If all these are not the same, or if then we know we have a solution to the Sudoku problem. Okay, we'll also define an XOR gate, and this accepts as a function, it'll accept as a parameter quantum circuit. The first qubit, the second qubit, or the inputs rather, and an output qubit in which it'll store whether or not the qubits are the same. And when we actually just draw it, this is what it looks like. We have 2 input qubits and an output qubit. And if these are the same, then as I've told you, this is going to be 0. And if they're different, this will be 1. So this is just, how to implement each portion of the circuit that I've already shown you. And as you can see, we have the checking circuit here with the Toffoli, and this is the full oracle. So the code for the full oracle is actually here. So as you can see, we have our variable qubits, which is the 4 qubits in that register. We have our clause qubits, and this is going to be another 4 qubits to store the outputs of our comparisons of the variables, and 1 output qubit. We have 4 classical bits because we're going to eventually measure 4 qubits and store the output of those in these classical bits. And we have a quantum circuit, which is made up of all 3 of these quantum registers in this 1 classical register. So the Sudoku oracle is just going to be defined taking in a quantum circuit, a list of the clauses and the clause qubits, and you can write it here such that it uses XOR to compare all the clauses in your clause list. And what it's going to do is it's going to do a multi-controlled Toffoli, and we do the uncomputing part. And that's how we get the Grover's oracle. Then we also have our diffusion transformation, because we're going to put this into Grover's algorithm. So it's just a copy of that diffusion function that we wrote above, except here I labeled the gate itself US. And now let's put all of this into Grover's algorithm so we can see how it solves the Sudoku problem. So we start by defining our variable qubits, clause qubits, output qubit, and our quantum circuit. Then we need to initialize the output qubit in the minus state. And we do that using the qc.initialize function. But if you wanted to do it manually, you just need to apply x and then h to the output qubit. without using this initialize function. Once we've done that, we need to initialize the qubits into a uniform superposition. So all the variable qubits need to be placed into a uniform superposition. Something important to remember is that the qubits that we're actually using in the Grover's algorithm are the variable qubits. The class qubits and the output qubits are sort of auxiliary qubits that we're using to help check the conditions. But we're only ever going to apply the diffusion transformation and measurement to the variable qubits. So by placing all of the variable qubits in a uniform superposition, once we've done that, we need to do iterations of our Grover's oracle and our diffusion transformation. So, of course, we can't, we use only 2 iterations, and we can't just automatically say, okay, we have 4 qubits, so the database size is 16. That wouldn't be a true statement, because not all values in that will satisfy the Sudoku problem. So, even if we're searching all 16 values, you might not necessarily need 3 or 4 operations of Grover's, of the Grover operator to actually get the solutions to have the highest amplitude. We can actually apply it, 2 times, and we get our solution. So that's what we're seeing here. The first iteration, we put in the Sudoku oracle and our diffuser. And then the second iteration will also be another diffuser, and then we measure the variable qubits and store it in our classical bits. And this is what the circuit will look like. So we place it in uniform superposition. Once we've done that, we initialize the output state to the minus state, and then we apply the Grover's oracle, which we've constructed above. We apply the diffusion transformation US, and for 4 qubits, you can actually see what this US looks like, because we actually already have a function to draw it. This is what that US looks like, but just to save space, we've only written it as this US there. And then we apply, again, another Grover oracle, which you can see here. One more diffusion transformation, and then we measure. So to run this circuit, we're going to use the air simulator. And to use the air simulator, you can just do air.get backend air simulator. And we're actually going to transpile the circuit. And transpilation in Qiskit actually simplifies your circuit, taking into account a certain number of parameters. I'm not going to go into detail on what transpilation does, but if you're interested, you can actually Google this or look for it in the Qiskit documentation. And then once we've done that, we're going to assemble our transpiled quantum circuit, and we're going to run it. So we're going to do simulator.run, and we'll run our transpiled circuit. We get the result, and we plot the counts, and this is what it looks like. So we see that the bit strings that we get that have the highest probabilities, these correspond to the solutions of our binary Sudoku problem. So it's important to note that we're using the little endian notation. So V0 is here and V3 is here. And as you can see, these actually correspond to the solutions of the Sudoku problem. So if, for example, if V0 is 0, V1 is 1, V2 is 1, and V3 is 0, we have, we're using the sort of diagonals, which I mentioned in the beginning. And as you can see, after 2 iterations of Grover's, we found the solutions to our Sudoku problem. And yeah, I mean, if you actually only do 1 iteration, you'll actually see that it already has high enough probability, but 2 iterations actually lowers the probabilities of all the other states that aren't solutions, and only keeps, with the highest probability, the 2 states that are solutions to the binary Sudoku problem. So that's basically how you can use Grover's algorithm to solve the binary Sudoku problem. And yeah, that's basically all I want to say for today about Grover's algorithm. And if you have any questions, feel free to ask them now, I think. Yeah.
Yeah, Ian, thank you so much. It was a lovely lecture, and thank you so much for the nice example of the Sudoku, because I never saw that before. So it was really very interesting. Thank you very much.